Welcome to lecture series. Today I will discuss about the concept of inverse linear transformations and also the concept of one onto linear transformations between two spaces, that is isomorphisms. We have seen what is LVV, the space of all linear operator on a vector space V. We have seen this is also not only vector space, it is also linear algebra. Now we want to see what is the meaning of a linear transformation is invertible. Okay. So concept of inverse linear transform. Let T be a linear transformation from V into W. T is said to be invertible if there exists a function, I am saying T inverse from W into V such that T into T inverse is a mapping, is basically identity. T into T inverse will be identity function. Here I am denoting IW means identity function on W, I mean from W to V please, and T inverse into T will be an identity function on V please. So T into T inverse will be identity function on W, whereas T inverse into T will be identity function on V. In fact, if you consider under what condition a function to be invertible, we know a function is invertible if there exists a f inverse such that f into f inverse is the identity functions. Here we are getting identity function over the W, identity function on the V, both different place. Here IW is not necessary to be equal to identity function on V place. In fact, I will say that T will be invertible if and only if T is 1 and onto. My claim is one thing, suppose T is a linear transformation from V to W and it is a invertible, then if I say that T is invertible, means there exists a function, I am saying the T inverse from W to V, and that function is again claim is it is a linear transformation also. So, let us say results, you can say small results, you can write in terms of theorems. Let T be a linear transformation from V into W, then if T inverse exists T is invertible, then the function T inverse from W into V is a linear transformation. See, here it is given me T is invertible. So, T inverse exists. Only thing that I have to prove that T inverse is a linear transformation from W into V. So, we have to prove to show T inverse is a linear transformation, that is for beta 1 and beta 2 belongs to W and C belongs to capital F, we have to show T inverse operating on C beta 1 plus beta 2 equal to C times T inverse beta 1 plus T inverse beta 2. So, I had to show this one. Given T is invertible, So, for beta 1 belongs to W, definitely there exists an element, say alpha, I will say that is again unique element, say alpha 1, because it is the function is T is 1 1 on 2. So, there exists an unique element alpha 1 belongs to V and alpha 2 belongs to V such that T of alpha 1 equal to beta 1 and T of alpha 2 equal to beta 2. Since T is a linear transformation from V into W, so C times alpha 1 plus alpha 2. So, T of this quantity will be C times T of alpha 1 plus T of alpha 2, because T is a linear transformation. So, this means that this is equal to C times beta 1 plus beta 2. So, T carries C alpha 1 plus alpha 2 to a unique element. So, I have C beta 1 plus for beta 2, there is a unique element in V whose image under T is C beta 1 plus beta 2. So, this implies that C alpha 1 plus alpha 2, which is equal to T inverse of C beta 1 plus beta 2. So, this is a unique element C alpha 1 plus alpha 2, which is basically image of C beta 1 plus beta 2 under T inverse. So, T inverse of C plus beta 2 equal to C times alpha 1. What is alpha 1? C times T inverse of beta 1 plus alpha 2 is T inverse of beta 2. So, T inverse is a linear transformation from W into V. So, we see that if the linear transformation T from V to W is an invertible linear transformation, then there exists a linear transformation from W to V, which is the inverse of T. That's fine. So, we have seen that. What is the meaning of inverse of a linear transformation, please? Let me define one more terminology called non-singular. A linear transformation T from V into W is said to be non-singular if it is 1 1. That is, for alpha 1 and alpha 2 belongs to V and alpha 1 not equal to alpha 2 implies T of alpha 1 not equal to T of alpha 2. That is, T of alpha 1 minus alpha 2 not equal to 0. So, T mapping from V to W is said to be non-singular provided T of alpha equal to 0 implies alpha equal to 0. So, this is the criteria for a non-singular linear transformation, please. Using this characteristic of the non-singular linear transformation, we can see some interesting results. What is that? Suppose T is a non-singular linear transformation from V to W. If I consider a linearly independent subset of V, what can you say about the image of that subset under T? Will it be linearly independent or not? These questions one can answer again by using the definition of non-singular linear transformation. So, let me just write in a formal way. This is small theorems. Let T be a linear transformation from V into W. T is non-singular if and only if it carries linearly independent subset of V into linearly independent subset of W. So, let me quickly prove this result, please. It will basically coming from the definition itself only. So, I have to prove both the ways, if as well as only if, because it is given to us that T is a linear transformation from V to W and T is non-singular if and only if it carries linearly independent subset of V into linearly independent subset of W. Okay. So, let me do first if part. It is given T is a non-singular linear transformation. Okay. Consider alpha 1 alpha 2 alpha k be a linearly independent subset of capital B. Claim T of alpha 1, T of alpha 2, T of alpha k is also a linearly independent subset of W. Suppose not, we will prove it by contradiction not. So, there exists k scalar C1, C2, Ck belongs to the field over which vector space V and W are defined. Assume that V and W here are defined over the field capital F. So, I have taken k scalar C1, C2, Ck belong to capital F such that your C1 T of alpha 1 plus C2 T of alpha 2 plus Ck T of alpha k equal to 0, where not all Ci I equal to 1 to k are 0. So, this is the hypothesis we have considered. Now, this implies that one can write down T of C alpha 1 plus C1 alpha 1 plus C2 alpha 2 plus Ck alpha k equal to 0. This implies sigma C I alpha I equal to 1 to k equal to 0. Why? The reason is T is, it is given to us, it is non-singular. So, according to definition, if it is non-singular, T of alpha equal to 0 implies alpha equal to 0. So, based on that I am getting this one please. But sigma C I alpha I equal to 0, I equal to 1 to k implies C I equal to 0 for I equal to 1 to k. Since alpha 1 to alpha k is a linearly independent subset of V. So, that is why each coefficient equal to 0, which contradict our hypothesis, contradicts our hypothesis. So, T of alpha 1 to T of alpha k, this set is also a linearly independent subset of W. Now, let me go for the only if. Given T maps every linearly independent subset to linearly independent subset of W. So, for 0 not equal to alpha belongs to V, certainly the singleton element alpha is a linearly independent subset of V. So, T alpha will be also linearly independent. So, this implies that T alpha is not equal to 0, or I can say that is, if T alpha equal to 0 implies that alpha equal to 0. This implies if T alpha equal to 0 implies alpha equal to 0. So, this implies T is non-singular. So, we say that if T is a linear transformation from V into W, T will be non-singular if and only if it carries linearly independent subset of V into linearly independent subset of W, please. Let me define one more terminology, please, which is also very important to understand the linear transformation or linear operator over a vector space, please. It is called concept of isomorphism, please. Let T be a linear transformation from V into W. T is said to be an isomorphism from V into W provided T is 1 1 and onto. If T is 1 1 and onto, then I will say that T is a isomorphism from V into W, please. And then V is said to be isomorphic to W. If a linear transformation is 1 1 onto, then it is invertibles. So, T inverse exists. So, T inverse exists means T inverse is also linear transformation from W to V, please. So, T inverse will be also 1 1 and onto. So, T inverse will be also isomorphism from W into V, please. So, if V is isomorphic to W, then W is also isomorphic to V, please. Let me consider some example, please. First examples, let V be a finite dimensional vector space over F and dimension of V equal to n. Then V is isomorphic to the space of n tuple over F, please. V is isomorphic to Fn. Let me solve it, that how V can be isomorphic to Fn, please. Given V as a finite dimensional vector space of dimension n. So, let B equal to alpha 1, alpha 2, alpha n be an order basis of capital V, please. Now, for any element alpha belongs to V, I can associate an n tuples. How? Now, for any element alpha belongs to V, I will be able to express alpha as a linear combinations of this basis element, that is alpha 1, alpha 2, alpha n. So, I can say for any element alpha belongs to V, there exist n scalars x1, x2, xn belongs to capital F, such that alpha equal to x1 alpha 1 plus x2 alpha 2 plus xn alpha n. So, for alpha there is a coordinate x1, x2, xn, where xi belongs to capital F. So, for each alpha I am getting a coordinate. This coordinate I can say belongs to n tuple space, belongs to Fn. Okay. So, for each alpha there is a unique coordinate x1, x2, xn belongs to capital Fn. So, this implies one can have a function say psi from V to Fn such that for each alpha I will have a coordinate, the corresponding coordinate say x1, x2, xn, which belongs to Fn place. Okay, let me say here one things. We have defined coordinate matrix of any vector with respect to given order basis place. Coordinate matrix there we have taken as a transpose of this coordinate, means basically column vector place. But here I am talking coordinate of a vector alpha, means basically n tuple place here. So, please do not confuse with this coordinate and coordinate matrix place. Okay. So, I see that if I define a function psi from V to Fn, like alpha goes to x1, x2, xn, we can show psi is a linear transformation and also 1 1 and on 2. So, that psi will act as a isomorphism between V into W place. Okay. So, linear transform characteristic of the psi we can check it like this. For any other beta belongs to V, there will be again coordinate of beta, let y1, y2, yn be the coordinate of beta with respect to given order basis. This is B. Let C be any element from the field capital F. So, C alpha plus beta, this is will be called to C times sigma xi alpha I plus sigma yi alpha I equal to 1 to n. So, this is equal to C times xi plus yi and alpha I equal to 1 to n. So, this implies that coordinate of C alpha plus beta is equal to I can write Cx1 plus y1, Cx2 plus y2, Cxn plus yn. This is equal to C times x1 xn plus y1 yn. So, this implies that coordinate of this is equal to C times coordinate of alpha plus coordinate of beta. So, this implies psi of C alpha beta is equal to C times psi of alpha plus psi of beta. So, psi is a linear transformation please from V into Fn. Psi is 1 1 and also on 2. So, you can do it as a homework please. So, we have seen then any finite dimensional vector space of dimension n over a particular field say capital F, then vector space is isomorphic to n tuple space over the capital F also. So, what is the benefit we are going to have through introducing this concept? Sometimes it is easy to talk the characteristics of this space instead of the corresponding space. If you go to the characteristic of corresponding isomorphic space, it will be easy. So, even though both the vector spaces, their vector additions may be different, their characteristics may be different, but they will preserve certain things. What are the things? If a subset is linearly independent in V, its image under the map, that psi, which is basically isomorphisms, psi of that subset will be again linearly independent in the Fn also. Already we have checked that one please, because psi is 1 1 on 2, it will carry the linearly independent subset to linearly independent subset please. So, it may be easy to check linearly independentness of the subset capital S. Not in capital V, you can check the linear independence of psi of S, which is in the W please. So, that is why this concept is very important please. We will talk more about this and utilize this concept in future lectures. Thank you.